welcome to my brand new playlist on algebraic proof for GCSE 9 to 1 maths. In each video in this playlist, we are working through sets of questions from past 9 to 1 papers from AQA and Edexcel. In each video, you can download the questions from the description of that video. Proof questions have a wide variety and also vary a lot in difficulty, so I've tried to get as many as possible to give you an idea as to what can come up. So here we have 5 questions. Let's do this. Hey there guys, welcome back to the channel. If this is your first time here and you're trying to get the best grade in maths you possibly can, let me help. Start now by subscribing. Okay, just quickly before we begin, I forgot to mention the golden rule of algebraic proof, which is to never just substitute numbers in. That doesn't prove anything, just shows that the thing either does or doesn't work for that number. Okay then, first up, n is an integer greater than 1, so a whole number greater than 1. We want to prove algebraically that n squared minus 2 minus n minus 2 squared is always even. Okay, so expanding brackets is very often the first step in proof questions, and it is here too. So we're going to want to expand n minus 2 squared. So we have n squared minus 2 minus the expansion of n minus 2 squared. So let's put that in square brackets. So n minus 2 squared, remember, means n minus 2 times n minus 2. So that's going to give us n squared minus 4n add 4. Okay, now we're going to let the negative into those square brackets. So we have n squared minus 2 minus n squared minus 4n, so that's add 4n, and then minus 4. So the n squareds cancel out. So we get left with 4n. And then we have minus 2 minus 4. So that's minus 6. Okay, now you may notice here both terms have a common factor of 2. So we can write this as 2 lots of 2n minus 3. Now we know 2n minus 3 is always going to be a whole number. And we know, because we're multiplying it by 2 on the outside, this is always going to be even. So we can then finish by saying, therefore, this is always even. In number 2, we have recurring decimals to fractions. Now this is usually a non-calc topic. The way they get around that, if they put it on a calc paper like this one was, they will say prove using algebra. Okay, so using algebra, prove that 0.136 recurring times 0.2 recurring is equal in value to 1 over 33. Okay, so we're going to want to turn both of these decimals into fractions. Now we'll do 0.136 recurring first because it's the trickier one to do. So to do this, we let x, you can use any letter, let x equal 0.136 recurring. Now, the first thing we need to get with this guy is a number on the right with a purely recurring decimal. So at the moment it's not purely recurring because the 1 does not recur. This means 0.1363636, etc. So the first thing we're going to do is multiply both sides by 10. Now I'm going to leave a little bit of space, so we get 10x is 1.36 recurring. Okay, and the next thing we need is another number with that exact same recurring decimal. So essentially we need to move the decimal point 2 places to the right. So we now multiply both sides by 100. So we're now going to get 1000x is equal to 136.36 recurring. Now the whole point of doing that is we can now lop off the recurring decimal using subtraction. So 1000x minus 10x is 990x. And on the right, 136.36 recurring minus 1.36 recurring is going to give us 135. Okay, now we need to get x on its own. So we divide through by 990 and we get x is 135 over 990. Now, the next thing we'd want to do is simplify this fraction. Given that it's on a calculator paper, you could stick it into your calculator. I'm going to try and do it without. So, we have a common factor of 5. So, 135 divided by 5 is 27. 990 divided by 5 is 198. Okay, now in that there is still a common factor of 9, so x is 3 over 22. Okay, so that's that side done. There's good news, 0.2 recurring is a lot easier. So, for 0.2 recurring, we're going to let y be 0.2 recurring. Then 10y is 2.2 recurring. Do the subtraction, 9y is equal to 2. So y is 2/9. Okay, so we now want to multiply 3 over 22 by 2/9. So that's going to give us on top 6. And on the bottom, 9 times 22 is 198. Now we have a common factor there of 6. So this does indeed go down to 1 over 33. We've done it. Okay, number 3. N is an integer. Prove algebraically that the sum of 1/2 n times n add 1 and 1/2 times n add 1 times n add 2 is always a square number. Only 2 marks. Pretty tight. So, sum means to add together. So, we want to do, we'll have 1/2. Now I'm going to expand the n with the n add 1. So this is 1/2 n squared add n. Add 1/2. Now I'm also going to expand n add 1 times n add 2. So that's going to give us n squared. Add 3n. Add 2. Okay, now if we expand with the halves, we're going to get n squared over 2. Add n over 2. Add n squared over 2. Add 3n over 2. Add 1. Okay, so now we need to sharpen this up. So n squared over 2 means 1/2 of n squared. So we have 2 of those. So n squared over 2 add n squared over 2 is 1 whole n squared. So this is going to start with n squared. Now we have 1/2 n add 3/2 n. Think of pizza. If you have 3 halves of a pizza, that means you have 1½ pizza. And then if you have another half, you have 2 whole pizzas. So n over 2 add 3n over 2 is 2n. And then we have 1 at the end. So how do we show that this is always a square number? Well, actually, we can factorise this to n add 1 squared. So whatever value n is, we're adding 1 to it and squaring, therefore this is always a square number. End of proof. Okay, next up, quite a tricky one. So this is really quadratic simultaneous equations. So we want to prove algebraically that the straight line with equation x minus 2y equals 10 is a tangent to the circle with equation x squared and y squared is equal to 20. So, just in case you don't know what a tangent is, let's do one of my best drawings. It's just about passable as a circle. A tangent is a straight line that only hits the circle at one point and one point only. So this is the situation we are trying to prove. Now we should start particularly with a 5-mark question. We should start with a statement that would explain how the straight line is a tangent to the circle. So the whole point of solving simultaneous equations algebraically when there's no real life context like cost or something like that, the whole point of solving simultaneous equations is to find intersection points either of straight lines or curves and straight lines or circles and straight lines. Now if this line is a tangent, then there will only be one set of solutions when we solve simultaneously. So we should start by saying something like if the line is a tangent, then solving simultaneously will lead to one set of coordinates only. So one x value and one y value. So because I'm going to run out of room, I'm going to delete that. Okay then. So, how do we start doing this? Well, what we need to do is use the linear equation to get one letter on its own in terms of the other letter. So, we have x minus 2y is equal to 10. So it's easiest and neatest to get x on its own. So we're going to add 2y to both sides. So x is equal to 2y add 10. Okay. Now the method that we use is called substitution. So we know the equation of the circle is x squared add y squared is equal to 20. Now what we're going to do is substitute this expression for x into the circle equation. So x becomes 2y add 10. So we're then going to have 2y add 10 squared add y squared is equal to 20. Now we want to expand 2y add 10 squared. So remember, this means 2y add 10 times 2y add 10. Make sure you can get 4y squared add 40y add 100 and then add y squared is equal to 20. Okay, so this is now a quadratic in terms of y. To solve quadratics, you always want to get everything on the same side with a 0 on the other. So we can sharpen up the y squareds. We have 5y squared add 40y. Now we're going to take this 20 on the right from both sides. So we're then left with add 80 is equal to 0. Okay then, now ideally, if we can, we want to now factorise this. Before you do that though, and this is a very common step with quadratic simultaneous equations, check for common factors. It's going to make life easier to cancel out any. So here, there is now a common factor of 5. So we're going to divide through by 5. So we're going to get y squared add 8y add 16 is equal to 0. Okay, so that looks a lot friendlier. So, we now want to factorise this, which factorises to y add 4 squared is equal to 0. Therefore, the only y solution is minus 4. Now, we could stop that and say, because there's only one y solution, there will only be one x solution, therefore the line is indeed tangent. Given that we've done all this work, I'm going to finish it off and also find the x coordinate. So, now that we know y is minus 4, remember that we also knew x was 2y add 10. This tells us then that x is 2 times minus 4 add 10. So that's minus 8 add 10. So that's 2. So the only point of intersection is at 2 minus 4. Now, a single point of intersection with a straight line and a circle means the line is a tangent. Okay then, fifth and final for this video, prove that x squared and x and 1 is always positive. Okay, so how are we going to do this? Well, x squared and x and 1 is a quadratic. So we need to think about the graph. Quadratics look like this. If this is always positive, then that means the graph never touches the x-axis. On the x-axis, the value would be 0. Below the x-axis, the value would be negative. So what we need to do is find in particular, the y-coordinate of the turning point, the minimum of the graph, which is the minimum value of the expression. Now the way that we do this is by completing the square. So x squared and x and 1. Okay, so to complete the square, you want a single pair of brackets with a square on the outside and an x on the inside. For now, we're going to keep that plus 1 on the outside. Now, whatever amount of x you have, you now half it and stick it in the bracket with the x. So we have 1x, half of that is a half. So we have x and 1/2 squared. Now whatever number goes inside that bracket, you square it and subtract it on the outside. So 1/2 squared is 1/4. So on the outside, we're subtracting 1/4. So we can write this as x and 1/2 squared, and then 1 minus 1/4 is 3/4. Now the coordinates of the turning point then so the x-coordinate is always the negative of the number inside the brackets, so it's going to be minus 1/2. And then the y-coordinate is just the number on the outside, so 3/4. So again, if we look at the graph, we can draw it a bit more accurately now. It's going to look something like this, where this point is at minus 1/2, 3/4. So we now know then the minimum value of the expression is 3/4. Therefore, x squared and x and 1 is always positive. Cool. Okay then guys, that's all the fun for this one. There will be lots more proof questions in the proof playlist, linked below in the description. If you found this useful, don't forget to give us a thumbs up, get subscribed to the channel, share with your friends. If you have any requests for topics you want done like this, let me know down below in a comment. For now, take it easy, take care.